All right, I'm up here at section 2.3 under basic energy concepts. And what it says is process. Define a process. Well, we just defined what state is, what state is of our working fluid, and how we defined that is if we can pinpoint the properties, we've defined the state, and if any one of those properties change, it's been a state. And then we described what phase was. And while we could have a state change, it didn't necessarily mean we had a phase change. If I was at 70 degrees atmospheric pressure and I raised it up to 71 degrees, there's a state change, but it doesn't turn to steam at atmospheric pressure if I raise it 1 degree. So there was no phase change here, but there was a change in state. A thermodynamic process occurs whenever our working fluid undergoes a change in state. So this right here represents some sort of thermodynamic process. And I'll bet you all can figure out what this process was. This was heat addition. There was a fire here that raised it up 70 to 71. The next thing we talk about, so that we understand what state is, what phase is, and what a process is. And we're going to be looking at 4 very important processes. The heat addition that's occurring in our reactor, and then the extraction of energy out of that steam in our turbine, then the heat removal in our condenser, and then finally the 4th one is the rise of pressure on our pumping system. That leads us to the first law of thermodynamics, section 3. First law of thermodynamics. First law of thermodynamics. And what that first law is very important. It's in bold right here on this page. Energy can neither be created nor destroyed, only altered in form. Excuse me. So if you'll recall, the energies that we talked about, we had potential energy, and we had kinetic energy for velocity, and we had pressure volume energy, and we had internal energy. Well, if I have all these energies flowing into a process, here's a process. I don't know what it is. Could be anything. It could be a pump, a turbine, a heater, a condenser. When I'm all done, I'm going to have probably some potential energy, some kinetic energy, some pressure volume energy, some internal energy, and it's got to be equal. Now, what I can add down here is I could add some heat in and some work out, but all of the energy into this process plus any heat that I add during this process has got to be equal to all of the energies out and any work done. It's crazy. You can't create it or destroy it. That's the first law of thermodynamics. And what I've introduced here is the term work. If I would have just put this, well, this unit here is BTUs, and I got an equal sign right there, and the unit for work is foot-pounds force. Because we remember work was force times distance. Well, there's a distance and there's a force. Well, how do I equate foot-pounds force to BTUs? And that's pretty clever. That is with this Joule's constant. That's what this J was right here. Joule's constant. And you'll see it on the right-hand side. Joule's constant states that 1 BTU is equal to 778 foot-pounds force. So I can convert between the two now. If I have a unit of work, I can convert it to BTUs with this conversion of 778 foot-pounds force. So the first law of thermodynamics is going to be important. Energy must be conserved. And there's some energies that are more important than others. We're not going to go hunting for, since we're not in the engineering world, but we might not go hunting for the ambient losses if we just assume that there's no ambient losses. As operationally oriented as we are, okay, that'd be a good thing. Are there times when we should be concerned if insulation has fallen off? Sure. So we may see excessive dry well temperatures because insulation has fallen off. Something that we should probably track down. Last unit that we talk about here during basic energy concepts is this old unit called a calorie. What is a calorie and why is it important to me? Well, when we talked about a BTU, we said a BTU was the amount of energy that you have to add to 1 pound mass of water to raise it 1 degree Fahrenheit. Well, a calorie is the amount of energy required to raise 1 kilogram of water by 1 degree Celsius. That's a calorie. One of the most important places we see it still, and it's kind of a remnant that's hanging around, is the Rodworth minimizer. Its design basis. Rodworth minimizer design basis. I know this is probably early on in your training, but if I asked you what the purpose of the Rodworth, got that backwards, little issues there, Rodworth minimizer, it's to minimize rod worth. So it is there in case any control rod, and remember, you guys might be new, but our control rod's coming from the bottom. So here's the reactor vessel bottom. If this control rod was to be drop out of the core, I don't want this rod right here to have too much ability to control the neutron population, such that I'm going to minimize its rod worth. And this thing here does that. Another name for it is called a rod pattern controller, but the design basis says if I were to get a rod drop accident, as long as the Rodworth minimizer is doing its job and I'm doing what it is suggesting I do, I will not exceed 280 calories per gram of energy deposition into my fuel cladding. So there's a remnant right there. There's where we might see calorie. And there's a design basis. And this is a need-to-know number later on in your program. It's the design basis of our Rodworth minimizer. Or newer plants have an RPC, rod pattern controller. That's a bad C, by the way. All right? And that's in a note there on the bottom.